How you doing? Sean Tech here again. Here to talk about Microelectromechanical System microphones, MEMS microphones. Now, on the lower left-hand part of your screen, you should be seeing a microphone chip, is what it is. On the right-hand side of the picture is the microphone chip, and on the left-hand side is the bottom of that chip. Sound will actually travel down into the port of the hole of the top part of the chip. Some microphones have it all down on the top. Some of them have it on the bottom. The bottom of the piece is what we call an interposer that has a metallic shell that's actually for this particular chip, which is a Knowles electronics. If I hover my mouse cursor over this, you'll see the name of the chip show up on there as well as the digit key number. This is a microphone that's made by a company out of Itasca, Illinois called Knowles, a large microphone producing company. It can be purchased on DigiKey currently in the 2020 April, March area for about $1 a piece. It gets cheaper as you order more of them, of course. But anyway, the MEMS microphone, I've actually got one of these right now. I wanted to find the good pair of tweezers that I normally use, and of course they are not to be found in front of me. Hashtag prepared, right? Hashtag prepared. Well, I don't see them here, and I'm not quite sure where they are, but I do have another one. I do have another pair in front of me that I can kind of use for this. There you have it. In my hands, try to zoom in close enough to where you might be able to see the hole, is the MEMS microphone chip. Now, what you are looking at, let me get rid of the website image on here. What you are looking at on the side of the or on the microscope picture right now is actually the pad layout for this on a circuit board that I've actually designed as part of a trial, as a sort of one of a class that I've currently running right now. Now that microphone chip, my goal is actually to remove the top part of the microphone to kind of show you like what's a little bit underneath the microphone. But in order to really do that in any way, shape, and form easily, I actually am going to have to solder this microphone onto the board. Now, if I were to place this microphone onto the spots here, and you can kind of see it a little bit better right now. In fact, you can kind of see a little bit of what's on the inside of the microphone, which we'll take a little bit of a closer look at here in just a little bit. You can actually kind of see it right in there. Now that microphone, just close out of a couple of windows here just in case something starts to alarm start to go off or something like that. I don't know. But anyway, so the goal is to sort of, if you were to look at this microphone sort of on its side, you would notice that there is a seal, and that's sort of hard to view right there. Let me put this down, increase my exposure up on the camera. Probably have to increase it up quite significantly so that you can really be able to see this here. I'll try not to cover too much of it up with my tweezers, but you can see that there is a most definite seal that goes around it. This seal is not too hard to break, but in order to do this correctly, I am going to need to solder it down onto the board so that I can remove it. Use all of this using hot air. Now, I've actually kind of done this in the past before a couple of times. I don't know how many tries this will actually kind of take with this. I've got a couple of spare boards to be able to work with, a couple of spare microphones, but my goal is to attach it down to the board, and then using a higher amount of hot air, remove the top part of it. So if you look at this right here, I really don't have much of a chance. I really don't have almost any chance to really get at the underside of the chip using a soldering iron. So instead, what I'm going to do is I'm going to tin all 4 pads of the SMT pad layout that I've got on my board, and then using hot air at a somewhat of a lower temperature while making sure I hold on to the interposer. That's the bottom part of the microphone that sort of attaches the inside parts to the pads. Just hope that I generate enough hot air to get the solder that the chip is made of to reflow first. There actually is, in some ways, a little bit of an easier way to be able to do this, is to attack with hot air coming from the bottom of the board. But I'm going to take the more dangerous route here and actually try to do this with a little bit more risk, so to speak. So this is a destructive test. I'm not currently wearing my excuse me, my wristband or anything like that. I'm just coughing into the microphone there. That sounds pleasant. Apply some flexing agent down to all 4 of the pads. A generous amount of flexing agent. This is surface mount, so flux is our friend. Here, I'm going to increase this a little bit using my Hakko soldering iron and some lead-based flux off of my spool. We're going to tin all of the pads. I got my soldering iron with my bent T15 tip over here set to about 650 degrees Fahrenheit. Now I'm going to make sure that I've got a nice tin tip, which I do. It's nice and shiny. I'm going to put a little bit there, a little bit there, a little bit there, and a little bit over here as well. Now that job is looking pretty good so far. Now a little bit more of the challenging part of this whole thing. It's easy to tin pads. It is harder to be able to attach this. So I'm going to turn my hot air pen down to about 300 degrees C. I'm actually going to turn it down a little bit further than that. I'm going to turn it to 275 degrees C is what it is. So now I've got my Hakko soldering, or excuse me, my quick hot air pen in one hand, which I'm going to apply some flexing agent down to the board while I preheat the board up. Okay, so I've got some flexing agent down. You should still be able to see it kind of on the screen here. Going to now get hot air going until I notice that my solder is starting to melt, which it is. Kind of waving it around a little bit. Apply a little bit of some heat down to there. Now I'm going to kind of just let it go and let it fall into its place. I don't really care too much about its the way it's mechanically attached, although it does look somewhat off-center, don't you think? I'm going to try to get surface tension to kind of blow that thing down into place. There we go. A nice and center position with that. That looks good. All right. So now I'm going to wait for this to cool down just a little bit. And actually, while it's cooling down, try to get into that center part. We're actually going to try and open this chip package up here in just a little bit. But you can tell there is something in there. There are actually 2 things on the inside of this chip. One of it being the transducer. Well, we would call the transducer. This is the part that turns our sound acoustic waves into an electronic signal so that a computer can recognize what it is. Very similar to how older traditional microphones work, as there's sort of a diaphragm that moves. This also has a diaphragm, although the diaphragm is much smaller and much more sensitive and not built out of the typical rubbery elastic material that we're normally used to using. So, okay, so let me zoom back out of it here. Let's see if we can pop this guy open with maybe just a little bit of some luck. I think we'll be able to do it. I'm going to turn my hot air up to 325 degrees C and increase airflow. Let's increase it to 95 here. This may not work. I'm hoping this kind of does, but this may not work. Actually, you know what? No, I'm going to keep it kind of low because I don't want to blow the chip apart here. I'm going to keep it actually down closer to around, say, 60, but increase the temperature up even higher than that, up to 340. This is a destructive test. I'm not looking to preserve anything or anything like that. I'm just looking to be able to take the top off the piece so we can take a little bit of a closer look. Okay, so now I'm starting to heat this up. I don't actually want flexing agent to be a part of this. You can see the solder on the bottom has actually already melted off, which is unfortunate. So the part is actually now attached, but I've actually been able to take the top part of it off, which is kind of a cool thing. So I'll put that kind of off on the side. You can see those little guys that are off on the side of the circuit board. You see these. Well, the biggest one is actually, I got a finer pair of tweezers here. That large thing that you see, the mass that's on there, is what we call a solder ball. Now, this solder ball is not something we typically want. It is now solid. It is not attached very well. As you can see, a little bit of a pluck actually removed it completely from the board, which is kind of a nice thing. But what you are actually looking at right now is the microphone itself. This is the part of the chip that turns the sound waves into electricity, and there are 2 parts on the inside of this. On the inside of this, let me zoom back out just so you can see. I've still got the lid here, So you see I've still got the lid, and this lid is very much just a shell. Oh, it is a shell that decided to fly away from me because I'm using a pair of tweezers that I don't normally like to use. I'm switching to my more grippier type of tweezers. You can see this is just a machined out shell that holds this. But upon looking at the inside of this with a little bit closer, you actually see that there are two devices, and I'm actually going to try and get a good shot of this here. I just realized that my gain is all the way up right now. I'm going to try and reduce down my gain just a little bit, which means I might need to bring up my exposure ever so slightly. There are a lot of features that have heights on this. So I'm going to first start with the bottom part of the circuit, which is what we would call that is the actual transducer. I'm going to try to get some additional light to show on this here. Okay, there we go. Now we'll try to do a little bit of a soft gain as we start to come up here. Let's see. Oh, that's looking pretty good. Okay. So what you are looking at right now on the bottom part of it, this small piece right here is what we would call the transducer, excuse me, not transistor, transducer. This is a silicon-based device to where if one were to look very, very closely at this, and there's probably no way I could really get up that close on here to really be able to kind of see the netting that there is, but there actually very much is a sort of net of holes, and you can just barely, I don't know if you can see that on there. Can you all see that? Can you see it like just around in the center like mass of the area, like this center mass of the area? There is, I'm gonna do my best right now. Like small amount of focus is gonna make this shake around a whole lot. So I apologize those of you who might be getting like, oh, I'm getting woozy, but you can just barely make out the sensor and the small spring diaphragm around it. I'm actually, what I'm going to try and do is I'm going to try and just capture a quick picture of that just as we, oh, that is a great, fantastic shot of that. I'll try to post that up on the something that we were actually looking at here. And actually, looking through my microscope, I can actually tell that the words that are up on the top of it say Knowles with a model number next to it, likely indicating the batch number of what we would call the die batch or wafer batch number. We'll get into a little bit more of that. But this, what you're looking at right now, is a single piece of silicon, what we would call a die, that is a small piece of that has a diaphragm that's on the top that as air flows past it, the diaphragm on top moves very, very slightly. We're not talking huge wavy increments of stuff or anything like that. We're talking about small movements on here which move up and down, where a bottom piece stays still. Now, there is an electronic phenomenon called a capacitor. Doc Brown may have invented this at some point in some movie, which is famous by some person or something like that. But either way, this is an electronic device that basically stores an electronic phenomenon called voltage and has a geometric thing to where its geometry changes the electronic property. And specifically speaking, it's built by two conductors with a sandwich of insulating material in between it, that if one of the conductors is moving, that makes the electronic property of the part actually move as well. So small mechanical movements actually create small electrical movements in the part. This die right here that you're looking at is functional very specifically just for that. This die, what it does is it moves up and down. That small annular part that's in the center of it actually moves itself up and down and creates a change in what we would call capacitance. Now, attached to this, I'm going to start to move this guy, again, ever so slightly. There are two connectors on it. Now, these connectors have a lot of height, so it's going to be very, very difficult for me to be able to actually focus onto one of these connectors, if any of these connectors, to be perfectly fair and frank. These are what we would call wire bonds. What you are looking at is a piece of gold wire that is probably on the order of around 25.4 micrometers in diameter, or about 1,000th of an inch in diameter, and it is welded to the from the actual transducer part of the microphone to the other die which is actually coated over with an encapsulation material. I actually can't see what's on it right now. I can only tell that there are 5 wire connections that are actually connected over to this die. But this is what we would engineers would abbreviate as the ASIC, the Application Specific Integrated Circuit. It is a chip inside the chip, or rather, you know how like some of the last videos we talked about like a chip being like one of I don't know, do I have one here? I usually have a million things. Do I got one here? I usually got one here. Is that one there? No, that's not one there. That's not one there. Egad, I don't have any chips. It's not a good sign. That's what that is. Is that one down over there? That looks like one right there. Oh yeah, that's one. So we talked about the last time these little buggers right here, what we would call chips. What you are looking at in my hand right now is sort of like the brain and the skull combined together. The actual thinking part is a smaller piece that's on the inside of it. What we're looking at right now is the electronic brain that makes the whole thing happen, what we would call an integrated circuit, an IC. Now, the application-specific integrated circuit is, I hope that landed in the right spot. The application-specific integrated circuit, the ASIC, provides all of the filtration, small amounts of amplification, and ultimately some protection for the actual sensor circuit, the actual transducer, what's on the inside of this chip. Now, the reason you can't see any of the fun parts of the chip, of the actual die itself, the ASIC die, is because it is coated over with an encapsulant material that allows things like moisture, water, our humidity coming off of our voices, and other kind of phenomenon to not affect it. Generally speaking, and you can take this from a lot of places, electricity and water don't combine very well. And we as human beings, I mean, you ever gone to a window and just gone in the wintertime? And what happens to the window? Your breath condenses because it has moisture on the inside of it, and it generally doesn't work very well with electronics. So the encapsulant material usually protects all of the electronics and provides a little bit of some other properties to it as well. But you can actually see on the inside that the die itself is connected up both to the sensor as well as with 3 additional wire bonds on the top that connect it down to the bottom interposer. The interposer is the part that we are actually soldering down onto the printed circuit board and forms what we would call the package, the microelectronic package, if you will. Both the sensor and the ASIC are, for lack of better words, glued, mechanically adhered down to the interposer, and then electrically connected to one another in the interposer, being these ultrasonic wire bonds, which we'll talk a little bit more about wire bonding at another time with it there, because it is actually a subject that I know something about. So what I'm going to get a chance to is just to show you what one of the inside parts of this chip actually looks like. In fact, actually, if you will, if you hold with me here, I've got it connected up to a circuit board that I've got in my hand here, which is a little bit smaller than a typical microscope slide. I'm going to try to actually get a little bit more of a 3D view of this, if you will. I'm going to try to hold it up on its side. Maybe. Will my helping hand work here? It's probably a lot steadier than my hand. My hand is is lacking in steadiness right now. So let's see here. Let me see. Can I get you? Can I get you to hold this? Is that okay? Is that all right there? Can you hold this? I just want to see if I can get a better shot of the overall interesting way that this kind of looks. Now that's kind of blurry right now. Let's see if we can fix that. Let's see if I can fix that just a little bit. Oh, that's pretty good. That is pretty good. That is kind of what this guy sort of looks like here. This is going to be somewhat hard to create a true focus on just the whole thing, because there's so many. I'm going to take a picture of that to see if that comes out a little bit better. Yeah, that's not too bad where it is. You can see the solder balls. You can definitely see the solder balls there, as they are sort of almost as big as the actual ASIC itself. That's the thing about ASICs and most die in general. For a limited functionality, such as a a basic, $1 microphone like this. You're not talking about anything really all that big. In fact, most ASIC, most integrated circuits for most common chip components that you'll find on boards are really no bigger than maybe like a couple millimeters by a couple millimeters on average. Not like everything with it on there, but take for instance the 555 timer that we've been working with. That IC is actually about 1 millimeter by 1.5 millimeters in its overall size. 1 by 1.4 if one were to look up the exact specifics with it. And I'm sure that varies with all kinds of stuff with it on there. Let me see real fast if I can get another shot. Oh, well, that's, hey, that's a nice picture. Well, can we look at something live on here? Would that be a little bit better? Maybe for to look at? Yeah, probably. Let's see here. I'm gonna try to turn the guy and put it down a little bit farther. Let's see here. Is that you? That's you. That's the helping hand. That doesn't help us if we were looking at that. There we go. That's definitely the microphone. I'm going to start to focus down. And there you can actually see a very good picture of what a typical microphone looks like. On the inside of a variety of devices, you can tell, actually, you can really tell from this angle the horribleness of how I soldered the thing down. I mean, I'm trying to destroy the thing, so all I care is that there's something mechanically attached to it on here somewhere. But really what you can see here on top of this is just the overall, really the size of this guy. The fact that this die right here, which, I mean, a majority of this particular die, the functionality part is actually all in this top block right here with a small piece of glass that is actually on the bottom of it that likely maybe has some sort of a hole drilled down and through it. It's actually a little bit tough to tell if that's actually glass or silicon from this view. It might actually be silicon now that I'm thinking about it, because there's no hole on the bottom of here, but it could be a couple of things. There's such a thing as called SOI, silicon on insulator, which is very likely what this probably is. You can actually see, if I were to zoom in just the right way and provide maybe a little bit of a better, maybe a little bit of some better lighting here. There we go. That is just a little bit better there. That actually looks really kind of cool. You can see the connections that are made to the MEMS, the Microelectromechanical System MEMS transducer, the sensor that's at the top part of it here, that go all the way down to the ASIC, and then the ASIC has wire bonds that go all the way down to the interposer, and they have this little arch that's within there as well. This allows things to expand and contract and have a little bit of some wiggle room as it goes with this. That's pretty neat to be able to see something like this. And of course, the better vision that I've got is actually in the microscope itself. So anyway, that's a little bit of an introduction to microelectronic packaging and ultimately kind of MEMS packaging as well. It's all really done on kind of on a small scale. It's an interesting part of the circuit here as well. So hopefully you got a chance to learn something new. Hey, are you folks interested in learning about potentially some other things or trying out some other things? Actually, maybe one of the things that we could do a little bit later on is actually build a circuit out of a couple of electronic components that I've got. That's something that I've designed that has one of these MEMS microphones on it. Might be kind of neat also, maybe at some point if we can, I don't know, maybe seal the thing up or something like that. It might be kind of a cool little show and tell thing to where we can maybe pop it open but still put it back down in there. I don't know though, that might be kind of tough to do. I don't know, it's pretty late on here. So anyway, let me know in the comments below if you're interested in seeing something, if you like this, if you don't like this, or just comment it and say, like, something else out there, something random or whatever. So but I will see you all on the next show. See you later.